So up until now, what we've done is we've talked a lot about point charges and how we calculate the electric field due to collections of point charges, how we calculate the electric potential due to collections of point charges. But point charges are not really how the world works. The world, at the level that we often care about it, is sort of smooth and continuous and has sort of distributions of things that are vary over some length scales and so forth. And so we have to figure out how to deal with charge when it's distributed in that way. So what we're going to do is try to figure out how do we calculate the electric field when charge is distributed in some continuous way. So the example that I'll give you is we have some blob here. And that blob has some charge distributed throughout it, right? So this is some three-dimensional shape that has charge kind of all over it, inside of it, and so forth. And what we want to do is figure out what the electric field is at some location, outside of the blob, right? And the question is, well, how do we go about doing that? Well, the approach that we're going to take is actually to leverage this technique of superposition, where we cut the blob up into lots of different pieces, and we treat each of those pieces as point charges. So if we sort of slice it up like this, and we treat each one of these little chunks as a point charge, where we have some separation vector associated with that one, and some separation vector associated with this one, and so on, we can calculate the total electric field by adding up all of the little chunks of electric field that we have by cutting it up into small pieces, right? So you could think about it as saying the total amount of electric field that we would be able to find at this point is a result of sort of adding up all the chunks and considering the electric field of each given chunk, right? That's exactly what superposition does for us. It helps us to figure out what the total field is due to some number of pieces, some number of contributions. Now, the challenge here is actually that how big of a chunk do you choose, right? How small does it need to be to get a good and an accurate description of it, right? And the idea behind that is that you want it really, really small. You want it as small as possible. So what we're going to have to try to do is we're going to have to take this to what we would call the continuum limit, where we essentially cut things up from, say, small chunks, delta Qs, if you will, so small chunks of charge, and instead think of those as continuously varying charges. And each little piece, like each little EI that we get from each chunk, is actually going to be a little bit of electric field due to some continuous amount of charge, some sort of very infinitesimal amount of charge. We'll call that dE. And so what we actually have is a very simple description of how each of these little chunks of charge work, right? So each infinitesimal chunk of charge, dq, which we'll talk about in a little more detail in another video, will contribute a total amount of electric field that is like a point charge of dq. So each one of them contributes exactly 1 over 4 pi epsilon 0 dq r squared r hat. Now this is very similar to what we did when we thought about point charges, because each one of these little r's is a different r, right? It's exactly like this picture here. We have to add up little pieces of r, or I'm sorry, add up little chunks of charge at different r's. But each of them contains an amount of charge dq. So we're going to unpack that and describe that in a moment. Let's make this a little more concrete, because this is kind of abstract and it's hard to sort of think about how this would actually work. So I'm going to erase this, and what we're going to do instead is talk about what happens in one dimension. So let's consider a really long line of charge, all right? And so this really long line, this is much longer than I'm demonstrating here. What we want to do is we want to find the electric field at some location, let's say here, okay? So what we would want to do is we'd want to slice up this line of charge into little chunks. So let's say, for the sake of argument, this is along the x-axis. Here's our little thin slice. The width of that little slice is dx. And that source, that little source there, is a distance r away from the point that we actually care about. So the game that we're playing is we're saying, okay, with this little chunk of charge, it produces an electric field, dE, that points like that, due to it having a charge dq, right? And then what we do is we just step along and we add up every little piece all the way along till we figure out what the total E is, right? So this exact setup where we have this little chunk of charge this distance away producing this dE is exactly this idea that each little chunk contributes a point charge of size dq. And then what we're doing is we're saying we'll move along and we'll pick a new chunk, which may have a different amount. Let's call it dq prime. And now we're at a distance r prime, and it contributes an electric field. It's closer, right? So maybe it's bigger, dE prime. And we would have to add up dE and dE prime along with all the other contributions along the way to figure out what the total electric field is. So what we're going to do is we're going to go through this example in detail to talk about exactly how we set this up, exactly how we think about dq, exactly how we calculate it for a given location where it's somewhat easier to calculate.